Now looking at some problems on projectile motion. The first one, we've got a stone being projected at an angle of 30 degrees with a velocity of 20 meters per second. So it's cast out at an angle of 30 degrees at 20 meters per second. So it looks a bit like that. And then it starts to move there. Taking gravity as 10 meters per second and the axis through the origin, the point of projection and the initial conditions are these. So when t is equal to 0, it starts at the origin. So that's why we're able to draw our diagram there. And our horizontal velocity would be 10 root 3, and our velocity vertically is 10. And we can get that, that's given to us, but really we get that situation by looking at our diagram for the projectile motion, which is at 20, that's 30 degrees, and you're able to look to get your horizontal velocity and vertical velocity. So if you work those out, you're able to get those two values from that triangle. That's where it comes from. So it wasn't just magically picked out of the air. What we want to do is find the greatest height reach. Well, we know the greatest height reach is the largest value of the position, but it's also where the velocity would be equal, the horizontal velocity would be, vertical velocity would be equal to 0. So what we're looking at vertically, we start with acceleration being equal to 10. Our velocity be minus 10 plus the constant. When t is equal to 0, our vertical velocity was 10. So we get 10 equal to minus 10 times 0 plus the constant. So the constant there is equal to 10. So there's our vertical velocity. Integrate again to get our position vertically. Gives us the integral of both those plus our constant. And when t was equal to 0, y was equal to 0, so our constant works out to be 0 as well. So there's our expression for that. Now, the greatest height we know occurs when dy dt is equal to 0. And if that's the case, we take the minus 10t plus 10 is equal to 0, and that must occur after 1 second. So what we need to do then, and we haven't done it, we need to take it back and put it into that function. So we get y would equal minus 5 lots of 1 squared plus 10 lots of 1. It's going to give us greatest height of 5 meters. Sorry, 5 meters. Not 5 meters per second. So there's our greatest height that's going to be reached by the stone there. Now the second part says the time of flight and the range of the horizontal in the horizontal plane. So the time of flight is going to be given to us by a situation where y would be equal to 0 because it starts there and it ends there. So our horizontal flight, our greatest flight, time of flight would be given to us by the positions where the y would be equal to 0. So we set up our function there equal to 0, and so we get minus 5t outside of t minus 2, so 0, 2, there's our two positions. And that sort of makes sense because if we're looking at that being a parabola, in terms that we know its greatest height occurred at when t was equal to 1. So you'd think it would complete its journey after t is equal to 2. Now, we want our range of flight in the horizontal plane. So how far did it travel horizontally? Well, we need our position statement for that. So we know our second derivative of the position, which was the acceleration happening horizontally, was 0. Integrate that, and we get our constant of integration. We just get a constant because 0 integrates to a constant. But our velocity horizontally was always 10 root 3. So that's where we get the 10 root 3 from. Integrate again to get our position. So it'll be 10 root 3 times t plus our constant of integration. Because we started at the origin, that would be 0. So when t was equal to 2, we sub that into that statement. We get 20 root 3 meters. So that's how far it travels in that 2 seconds. Because it started at 0, finished at 20 root 3. So that's where we get our position and our range of in the horizontal plane. This time we've got a body projected into the air with an initial velocity of 50 meters per second, so it's looking like that, at an angle of theta, and this time we're told theta is inverse tan of 4 and 3. We're told to take gravity as 10 meters per second And then we want to find the velocity and direction of the motion after 1 second. So what are we talking about here? So we want to look at the idea that in our diagram here, what will we have? We have 50, if it's 50 there, and we know tan of theta is 4 and 3, those two sides, the vertical velocity and the horizontal velocity, must be in the ratio of 4 to 3. So if that's 50 degrees, and working with our trigonometry, our vertical velocity must be 40, our horizontal velocity must be 30 at the initial point. So horizontally, we know we start with our acceleration being 0. We integrate to get our constant, and our constant in this case would be 30 degrees. So the horizontal velocity is always 30. Our vertical velocity, however, we know acceleration vertically will be minus 10 because it's gravity, it's acting down. So we integrate that to get our vertical velocity. Now, if we get the minus 10 times t, because we integrate minus 10, we get our constant integration. And we know initially that when t is equal to 0, our vertical velocity is 40. So we sub that in, we get our constant integration being 40. So our velocity statement must be, for being vertically, minus 10t plus 40. So there's our two statements there that gives us our velocity both horizontally and vertically. Now, after 1 second, so the particle's travelled, it's actually at a new angle there. So what angle is that? Well, we know after 1 second that the horizontal velocity is still 30. Our vertical velocity is 30 now, because we can sub that one into the vertical velocity statement, and we get that being 30. So this gives us this triangle here, which must give us a 45-degree angle. And to work out our velocity, we can either use trigonometry or we can use Pythagoras' theorem. And our velocity now has become 30 times root 2 meters per second. So that's what our velocity is after 1 second. Horizontal velocity stays the same. Vertical velocity obviously is slowing because the particle's rising, but gravity is acting in a downwards motion. So it's going to slow that particle up. Now we want to find the Cartesian equation trajectory of the body. Well, to get a Cartesian equation, we need to relate the position statements for x and y. So we go and integrate again from our horizontal and vertical velocity statements. So we integrate 30 gives us 30t. We know when t was equal to 0, x was equal to 0, so our constant there would be 0. And that gives us our statement for its horizontal position at any point in time. Vertically, we get, we knew we had minus 10t plus 40 as the velocity. We integrate that, we get minus 5t squared plus 40t plus the constant, another constant. But because t was equal to 0 and y is equal to 0, our constant's equal to 0, so we get y is equal to minus 5t squared plus 40 as our vertical position. Now, we want to find our Cartesian equation, which means we want it in terms of x and y. So we have to, it's like a parametric, we've got a parametric form here, and we want to get back to our Cartesian form. So we let t be equal to x on 30, and then do the substitution in. So we get x squared, x on 30 there, and clean it up. We square that and do the division, and we just cancel the 10s there. Gives us our position statement there. Third problem. Particle is projected at 45, velocity of 15. So 45 degrees at 15. That'll allow us to get our vertical and horizontal positions, because we can say the vertical velocity or horizontal velocity would be cos 45 is x dot on 15, so x dot would be 15 cos 45, or 15 on root 2. Because it's 45 degrees and it's right angled, they must be exactly the same. So y dot, or the vertical velocity, is 15 on root 2. Allows us to start getting our equations of horizontal and vertical displacement, because we know we start off with the acceleration being 0 for horizontal. The horizontal velocity is constant, so that'd be our 15 on root 2. And then integrate again to get our position, and we get t plus the constant, And because we start at the origin, it doesn't say, so we assume we take our starting point as the origin, and then our constant would be 0. So the x position would give us 15 on root 2 times t. Vertically, we know we start with minus gravity, and we're taking g as 10. Integrate to get minus 10t plus the constant, and we know when t is equal to 0, our velocity is 15 on root 2, so we can get our constant being 15 on root 2. We integrate again, so minus 10t becomes 5t squared, 15 on root 2 becomes 15 on root 2t, plus our third constant, and again our vertical position started at 0, so our constant there for C3 was 0. So there's our displacements for both horizontal and vertical. Now find the time taken to reach the ground. Well, to reach the ground, we know that velocity is y is equal to 0. So we set that up as equal to 0. We get t is equal to 0, which makes sense. That's where it started from. And then 3 on root 2. So then that means it takes 3 on root 2, or if you want to clean it up and get 3 root 2 on 2 seconds to reach the ground there. So that's starting to put together our equations, getting our horizontal and vertical displacements, starting from the acceleration, and then starting to solve some problems that are involved with that.